Welcome back. Now I'm going to derive the describe function for a specific nonlinearity. Let me pick the first example, very simple example, which is on-off nonlinearity. So on-off nonlinearity. You may find different approach in different books, but what I follow to derive the describe function for different types of nonlinearity, I will try to explain to you. So what is my objective? Objective is to find out the describing function. Now what is describing function? I already explained to you that describing function is the ratio between amplitude of the fundamental component of the output and to the fundamental to the amplitude of the input sinusoid and their phase difference. Now fundamental component means a1 cos omega t and b1 sin omega t. Now you have seen the amplitude of the fundamental. I have already derived that amplitude of the fundamental component means root over of a1 square plus b1 square. Now and also angle is phase angle is tan inverse a1 by b1. So only you require the value of a1 and b1. Now question is that the formula according to the formula of a1 and b1, they require yt. Now what is yt? Yt is the output waveform of the nonlinearity. Now I am considering this case is a on-off nonlinearity. Okay, it's a on-off nonlinearity. So if I consider the block and if the describing function is capital N, so then input is x equals to capital X sin omega t, output is y. Now if it is sinusoidal, input is sinusoidal, then output must be periodical, but not necessarily be it is sinusoidal, but it must be periodical. Now what type of output waveform shape is, because depending on the shape of the output waveform, you have to check that the output waveform is having order wave symmetry or even wave symmetry. Now the nodes regarding order wave symmetry and even wave symmetry and quarter wave symmetry I have already attached in the Google Classroom. I'm not going to discuss about the different types of symmetry in the various waveform. You can find out this symmetrical waveform, symmetry for finding out the symmetry from the waveform. You can find out these theories or topics in the circuit theory books in the Fourier series chapter. So I'm in this page I am going to draw the output waveform. Now I'm taking the case of on-off nonlinearity. Let me draw the characteristics curve of on-off nonlinearity. And on-off any characteristics curve of different of a specific nonlinearity is always drawn with respect to x-axis and y-axis. And you know that for this case of characteristics curve, x-axis denotes input and y-axis denotes output. X-axis denotes input and y-axis denotes output. Always remember. So first of all, let me draw the characteristics of on-off nonlinearity. X-axis is input and y-axis is output. What is on-off nonlinearity? On-off nonlinearity is this. This is the characteristics curve for on-off nonlinearity. Say the on value is capital N, and for the negative case it is minus n. So that means that when the input is just greater than 0, the output is m. When the input is just less than 0, output is minus m. Now after drawing this characteristics curve, always remember I follow this before I draw the input waveform and output waveform. My objective is to find out the output waveform. I don't know what is the shape. Is it square or triangular or trapezoidal? So I'm going to draw, there's a technique what I am going to follow, and I will draw the output waveform. So before I draw the output waveform, because output waveform is required, before without having output waveform, we cannot find out the symmetry. We cannot take the advantage of symmetry. That is, if for you know that for odd wave symmetry, A1 must be 0. So if you find out the symmetry, there is no necessary to find out A1. You are only required to find out B1. So in this case, the amplitude of the output waveform only to the power of V1 square. That is only V1. So that's why I'm going to draw the output waveform. But before I'm going to draw the output waveform, first of all I must draw the characteristics curve. And remember, this is input axis, this is output axis. Okay. Now I am going to draw the waveforms. This is not the waveform, right? This is the characteristics, and the characteristics is drawn with x-axis as input and y-axis output. Always remember, do not be confused. Now I am going to draw the waveform, and waveform waveform also requires x-axis and y-axis, but waveform requires x-axis to be input to be time axis, and y-axis is the amplitude. So to draw the waveform, I require the x-axis to be time, and y-axis is the amplitude. First of all, I will draw the input waveform, and you know the input is sinusoidal. So it is say xt. Xt is what? Xt is input sinusoid. Now input sinusoid is having capital X as amplitude and omega as the frequency. So this is the amplitude, and say this is time 0, this pi is 2 pi. So this is the input waveform. Okay, this is the input waveform, and input waveform is xt. Okay, input is xt. Now I'm going to draw the output waveform, which is yt. Yt. Okay, output waveform yt. So I don't know what is the kind of shape of the output waveform. So before drawing the before I draw the output waveform, first of all draw the projection from the input waveform from the time axis. So what are the projections? Now the projections are nothing but the zero crossing points of the input waveform. The input waveform, this is the sinusoidal input waveform. It is crossing the zero at that point pi, at the point 2 pi, at the point 2 pi plus pi, that is 3 pi. So these are the projection from the zero crossing point from the input waveform. Now xt is the function, okay, input function, which is sinusoidal. Now yt, what about yt? Now from the input, in this case also, see, input denotes along the characteristics curve, x-axis is input, which is xt, and along y-axis it is output, which is yt. Now when xt along, if you very carefully watch the characteristics curve, because uh, the actual background of drawing the waveform lies on the characteristics curve. Now see, when the input, that is xt, is just greater than 0 along this axis, the output, which is yt, becomes m and stays m as long as the it is positive. Now you see, this is xt, okay, this is xt, this is also xt. Along the characteristics curve, this is the input, which is xt. Along the waveform y-axis, this is xt. Now condition is that when xt is just greater than 0, xt is just greater than 0. Check, xt is just greater than 0. Now xt is greater than 0 for the whole positive cycle of the sinusoidal. Xt is greater than 0. Xt is greater than 0 for whole positive cycle of the sinusoidal. Now as long as the along the characteristics curve, as long as the xt is greater than 0, the output is on. So since the input waveform, which is xt, is positive for a whole positive cycle, then we can say that the output waveform is just m, stays m as long it is positive. Now this is the input is positive for the positive half cycle, because this is also xt, this is also xt. In this case, for the characteristics curve, this is the input, but for the waveform, this is xt, this is the input. Along the characteristics curve, this input axis is actually representing this input of the waveform axis. Now if I consider the characteristics curve, input is greater than 0 for all the input is greater than 0, means that input is greater than 0, and input is greater than 0 for the positive half cycle of the sinusoidal. As long as the input is greater than 0, the output is on. That's why output is on. Now whenever it goes to negative, the input becomes negative. The input becomes negative. When the input becomes negative, the output becomes also negative. But it's minus m and stays at minus m. So the amplitude of the output waveform is now m and minus m, and so on. So you obviously find out that it's kind of square waveform type shape. It's not maybe square. It may not be square waveform. It may be rectangular, but there is a periodical waveform, and that is how we can find out the this is the output waveform. That is how we can find out the output waveform from the characteristics graph and the input sinusoid. Now after having the output waveform, you have to find out the value of a1 and b1, because ultimately you have to find out this describing function. To derive the describing function, we require a1 and b1. Now you can take the advantage of symmetry in case of Fourier series. Now this waveform is symmetrical, and this symmetry specifically odd wave symmetry. Now how to find out odd wave symmetry and even wave symmetry, you can find it out from your book. Since odd wave symmetry means that in this case odd wave symmetry, because with respect to a zero axis, with respect to a zero crossing point, this is symmetrical first of all, and if it is positive, then it is negative. So it's basically odd wave symmetry. The value of before the zero crossing point, if it is positive, after the zero crossing point, it is negative. Better definition you can find out from your book. How to find out what is the definition of odd wave symmetry and even wave symmetry, mathematical representation of odd wave symmetry and even wave symmetry. But however, I can find out that it is odd wave symmetry, and so since it is having odd wave symmetry, before saying that it is odd wave symmetry, since it is symmetrical, so there should be no DC component. So however, we write down a1 as y1 as a0 plus a1 cos omega t plus b1 sin omega t. but since it is symmetrical waveform, that's why a0 is 0. And okay, let me write since yt is symmetrical, and since it's the yt's output waveform is having order of symmetry, so a1 must be 0, since yt is having order of symmetry. So only you require to find out b1 component. So yt is left as only uh, b1 sine omega t. So only you have to find out the value of b1. So not, it's not required to find out a1 in this case, and that's the advantage of symmetrical waveform. Now again you see that b1, what is the formula for b1? b1 is 1 by pi integration 0 to 2 pi yt sine omega t d omega t. What about yt? In between 0 to 2 pi, so you have to find out b1, and in between 0 to 2 pi, that means in between 0 to 2 pi, what is the condition for yt? Rather from integration, I can write down, I make it more simple by writing 2 by 2 by pi integration 0 to pi yt sine omega t d omega t. You can keep it 0 to 2 pi, but I want to reduce the integration computation of integration. That's why I am reducing the using the help of mathematics. I am reducing the limit of the integration 0 to pi. So what does it how does it help me? So if I consider only 0 to pi, then I have to check the condition only about 0 to pi. Now from 0 to pi, what is the value of output? Yt. Yt is always m 0 to pi. So I can write down yt is equals to m for 0 omega t less than equals to pi. So omega t is, if the axis is omega t, the omega t is less than is in between 0 to pi, then yt is m. You can also keep your integration 0 to 2 pi. In case of, if you keep your 0 to 2 pi, then you have to check, you have to keep break the integration from 0 to pi, then pi to 2 pi, and 0 to pi it is plus m, pi to 2 pi is minus m. Thus result will be same. But I am reducing the computation of the integration. That's why I am reducing using the help of mathematics. I am reducing the limit of the integration. Now I can put it the value of yt in the integration 2 by pi integration 0 to 2 pi in 0 to pi yt is equals to m in this limit. So m sine omega t d omega t. Now m is constant, so 2m, keep your m outside of integration. So 2m by pi integration 0 to pi sine omega t d omega t. Now integration of sine will give you minus cos omega t. Limit is 0 to pi. So the value will be 4m by pi if you put the value of limit 4m by pi. So in this case, what is my output y yt. Yt I rather write as y1t because I am keeping only the fundamental components. That's why I can write in y1t. Y1t is found to be what b1 sin omega t is already, because due to auto symmetry a1 is out, so b1 sin omega t. Now y1t is equals to b1 is already found, b1 is found to be 4m by pi, so 4m by pi sin omega t. So what is the Describe function? This is the output waveform, and you know that the Describe function n, the formula you know, that root over of a1 square plus b1 square by x at the angle of phi. Now you see that a1 is there, here is no a1, so only b1, so root over of b1 square by x at the angle of phi, so only b1 by x at the angle of phi. Now b1 is found already 4m by pi, 4m by pi, so it is 4m by pi x at the angle of phi. Now what is phi? Phi is the phase difference between input and output. Now output waveform is also having sin omega t, input waveform is also having sin omega t, so there must be no phase difference, so phi should be 0. So 4m by pi, so Describe function for the on-off nonlinearity is 4m by pi x at the angle of 0 degree. I hope that you have understood that what is the phase difference. Phase difference is the difference between the output waveform and the input waveform. The output waveform is having amplitude 4m by pi, but frequency is same omega. The input waveform is also having same frequency omega. However, the amplitude is same. But the same waveform omega t, sin omega t is also sin omega t. So there is no even sin omega, there is no expression like sin omega t plus something. So there is no chance of phase difference between output and input. So there is no phase difference. That's why the phase difference is 0 in this case. And this is the describing function of on-off nonlinearity. And this is the way you can find out the describing function for different types of nonlinearity, for different types of characteristics graph, whether it is on-off with dead zone, or saturation, or hysteresis, or backlash, whatever your characteristics graph. If you follow this procedure, you can find out if you are able to find out the output waveform, then you check the is it symmetrical or not. If it is symmetrical, then it's check that is odd wave symmetry or even wave symmetry. If it is odd wave symmetry, then a1 is 0. If it is even wave symmetry, then b1 is 0. If it is not symmetrical, then you have to find out a1 and b1 both. And like in case of backlash, you will not find out any kind of symmetry, so you have to find out a1 b1 both. After finding out a1 and b1, you have to find out the ratio between root over of a1 square plus b1 square by x, and also find out the phase difference. And that is the n, which is the Describe function. After having the Describe function for all the nonlinearities, we will move to determine the stability using Describe function method. Now I suggest you to follow my method and try to find out the Describe function. Try to draw the output waveform for all the different types of nonlinearity by yourself. If you find out any problem while drawing the output waveform for various types of nonlinearity, I will suggest you try to draw the nonlinearity for saturation, dead zone, then on-off with dead zone, then hysteresis, backlash. And if you find out any problem while drawing the particular waveform of a particular nonlinearity, you can give your comment on the Google Classroom. I will address this your problem while drawing the output for a specific nonlinearity in my next video. So I hope that it will work for you. And it's raining outside, so good night.